All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you guys are okay, had a good weekend. We had a test at the end of last week, as I'm sure you guys remembered. I sent out the grades a little bit earlier today, so we're actually going to talk about that for a little bit, I guess. Yeah, so you should already see the grades, so you should know what you have. There is still a little bit of confusion, though. I do still have people getting confused about how the grading is done and whether or not bonus points count or things of that sort. I've been getting some emails. So again, bonus points are extra. They can only help you. They cannot hurt you. So if you don't do the bonus problems, it doesn't matter. You can still get 100%. If you do, you can get extra. You can get over 100% in theory. So the bonus points can only help you. That being said, when we're in grade scope, I make the bonus points count as if they're real points, but that's just because I don't want to miss anything. If I don't let the bonus points count in grade scope, then I'd have to manually check each individual student and manually add up how many bonus points you get. And that just takes too much time. So I make sure that grade scope counts the bonus points as if they're regular points. However, when I transfer your grades to Jupyter, which is the only place that you should be looking at your grades in, I change the denominator of how many points the test or the quiz is out of. And so your real grade is on Jupyter, right? So it's possible that you can get 100%, but on Gradescope, it doesn't show 100%. That's because the total includes the bonus points. But when I transfer it, I actually make sure the total is out of the right thing. So yeah, there's still some confusion on that. So I just wanted to mention that. That being said, let's actually talk a little bit about the test. Well, not really about the test, but I guess about how the class is doing overall. So as the instructor, there are kind of two points of view that I have or I have to have. So of course, one is, of course, I care about you all individually, but it's also very important to me as an instructor, how the class is doing overall. So if I pretended the entire class was one person, how would that person be doing? And as you can see here, this was what the grade distribution looked like before the test, as well as before the homework. So it shows that there's a test grade right here, but I didn't actually put the test grade in yet. So this is just before the test of how everything was looking overall. So as you can see here, the class average is a B, which is pretty good, a little better than average for my class at this point. So at this point, you guys had 7 quizzes, and that was the only thing that was going into your grade. I dropped 2 of those quizzes. And so this is kind of what it would looks like going into the test. As you can see here, there are like 10 people with an A or an A minus, and there are like 22 students in the class. So we had close to 50% of the class having A's, which is, yeah. And then everyone kind of spread out afterwards. Things became a little bit more bimodal after the test, which is expected. You expect people to actually do a little bit worse after the first test, just kind of getting accustomed to everything and having a different kind of testing stimulus than you're used to. So after the test, here's how things looked. So now you see that there are 2 peaks. And overall, the average is still a B, right? Which is why, for those of you who know about statistics, just knowing the average isn't good enough, because if I just talked about averages, students always want to know, what was the class average? What was the class average? The class average was the same before and after the test. However, clearly this class is doing better than this class, right? Even though the class average is the same, clearly there's more disparity here. So what kind of happens is now that we have 2 peaks, after the test, we had a very distinct grouping, right? So we had a bunch of people still doing well. In fact, exactly half of the class currently has an A or an A minus. So it actually even went up a little bit. So we have 11 people with an A out of 22. Literally like 50% of the class is getting an A. But then we don't really have anyone in the middle, barely anyone in the middle. But then I have a lot of people also congregating down the D side of the spectrum. So at least we can be thankful that no one's at an F currently. Some of you are borderline though. And this is what is overall. I've already put in the homework. And remember, for the homework, if you get a minimum of 85%, I bump that up to 100% automatically. So you get 85.0% on the homework. I type in 100% for your homework grade. And both the homework and the tests are put in here. So yeah, and this is the overall distribution right now. And this is sort of what the distribution looked like for the test as well. So I had a bunch of people getting around 80s, and then another bunch of people getting around 40s. So there was a definite split there. And I had very few people in between. So the average for the test was, I don't remember, in the 60s somewhere, mid to high 60s. And then, now the average for the class, because of the homework bump and the quizzes and the fact that I dropped 2 quizzes, overall the class did a little bit better than the test. But the test actually looked, in terms of the shape of the test, this is more what it looks like. So that's kind of where we are overall. Not bad. I'm sure some of you aren't happy. And I already have some people requesting office hours from me, which is totally fine. You want to talk about your grade, why you got that grade, how you can improve over time. Definitely reach out. Don't just retreat into your corner and give up. Definitely reach out and let me know. However, after class today, I have office hours, and I'm also booked after class on Thursday. I probably won't be able to meet this particular week. I won't be able to meet with anyone on Wednesday or over the weekend. But tomorrow on Tuesday, I think I would have time to meet a few people mid-afternoon onwards. So yeah, so if you want to schedule an office hour with me, you can actually do that. Just send me an email and we'll try to figure something out. So for this week, it looks like Tuesday, first come, first serve is where you're going to get. But that's how we're doing overall. So like I said, overall, I'm happy, but it's still not. It's a very cautious kind of happy. I'm sure it's like half the people are unhappy. You know what I mean? So it's kind of like, we're okay, we're all right, but we could do better. And this is one of the reasons why. So this is now a couple of reasons why I try to set up another avenue for you guys to actually have a resource, which is Piazza, which no one is using at the moment, but it is a place where you guys can actually get together and tackle problems. I even posted a question there myself to see how you guys would respond to it. It's scary. It's really not scary. It just looks different. If you get in, it's really fine. If you need help posting a question on Piazza or something, I can probably do some sort of demonstration or something. That being said, yeah, what I wanted you guys to do is to be able to talk to each other. You know what I mean? Like I said, half the class is doing well. It would be nice if I can get that half of the class to help the other half of the class. So it's not just Jhevon who's talking to you. You have to learn this. You can talk to your peers. You can get help from each other. You guys will probably know how to explain to each other better than I can explain to you all at once. So it's a nice thing to have. Just think of it as an extra forum, a public forum that we can go to and we can discuss things, as well as, it's somewhat supervised. So if you ask a question on Piazza and a bunch of students answer your questions, I can come by and I can endorse the answers and I can say, okay, this student know what they're talking about, so they told you the right thing. I would tweak this answer this way, or I would, so I can actually have you guys help each other, and I can kind of summarize it at the same time. So, I won't miss anything in emails, and you guys can get help even when I'm not available. I think it's a really good thing to actually get into. So you guys should look into that. So yeah, overall, that's how things are at the moment. so I just wanted you guys to just have an overview. Let's get back into the topic at hand.
Can I ask a quick question?
Yes.
You mentioned that we might be able to go over the test in recitation on Friday. Is that still the plan?
Yeah, and it would depend on just how far you guys get on Piazza and stuff like that. So the recitation on Friday, no quiz, right? So you don't have any graded work. So use that opportunity to catch up. You can also talk about series stuff in the recitation. So the stuff that we do today and Thursday, anything that you want to catch up on, you can talk about that if you guys already get through the test. So it'll be a combination of those or one of those. I would recommend, right? So either go over the test, make sure you know why things are the way they are, and if you have time left over, you can talk about sequences in series, whatever we've covered so far. Okay. That being said, let's jump back into it. Let's do a quick recap, just very quick recap, because, series, while I don't think it's difficult per se, it's something that's new and it's unlike anything that we've seen before. So a lot of people get weirded out because something is scary, just like how he's like, Piazza is scary, right? Because it's new. So I like to do a lot of recaps here. So let's just do that. Sequences is where it all started for us. A sequence is just a list in definite order. So for us, it means a list of numbers in a definite order. So there's a way to talk about who comes in what place in the list. We will be focusing on infinite sequences, and there's the idea of the convergence of an infinite sequence. And this basically just means if you take the limit as n approaches infinity, it will approach some real number value. If it does not, you say that the sequence diverges. So we did some examples of sequences there, blah, blah, blah. We looked at properties of sequence. So sequences obey all the familiar limit rules that you had from calculus 1 whenever they are convergent. There's also the idea of a decreasing sequence, meaning that the dots move down as you go from left to right. A couple ways you can identify that is if you can show that the n plus first term is always smaller than the nth term. So once you have a term, the very next term is going to be smaller than that. Sometimes that's obvious to see, sometimes not. Another way you can do that is to find the derivative and show that it's negative. One or the other, as long as you can demonstrate this, you can prove that a sequence is decreasing. Knowing that a sequence is decreasing is actually important. We'll actually talk about that today. So the reason why I gave you this definition, you'll actually see that today. All right, then we moved on to series. So a series, the definition for us, this is just the sum of the terms of a sequence. So it's like you have a list of terms, they are in a definite order, but now you want to add everyone in the list. This is very important for all sorts of applications. In fact, in calculus 1, the integral itself is such a series. It is a Riemann sum, right? And you want to be able to add up an infinite number of things. So for example, again, the Riemann integral is an example of such a series. You add up an infinite number of areas of rectangles, and that tells you about the area under a curve. You wanted to generalize this idea, and we want to do it in such a way that definitely makes sense and that is reproducible and is mathematically logical and consistent. So we define what a series is, just the sum of the terms of a sequence. The sequence, again, can be finite or infinite, but we only care about the infinite ones, and therefore we care about infinite series. And we realize that a series, we can say a series converges, adds up to something meaningful, if the sequence of partial sums converges or adds up to something meaningful. What does that mean? Well, if you keep adding term after term of the sequence and just like slowly compiling the sum going forward, and then after each step, you write down that number and put it in a list and create a sequence, right? So this is sequence of partial sums. So the partial sum, Sn, is just the sum of the first n terms. So S1 is the sum of the first term. S2 is the sum of the first two terms. S3 is the sum of the first three terms, and so on. And it cumulatively builds up. you can build a sequence with those guys. And if that sequence converges, we say that the overall series converges, meaning that this infinite sum or whatever will add up to something meaningful. And so that's what that means. We did an example of that where here we had this infinite sum. We constructed a sequence of partial sums. We took its limit. And so for us, it meant that the series converged to 1. There's also the notion of absolute convergence. That was very important. This basically just means if I put absolute values around all the terms, the series still converges. That's important because if that does not happen, I should probably mention the other one, right? So absolute convergence is when if I put absolute values around each of the terms, we add them up and it can still make sense in the way that we meant before. However, if when I put absolute values around it, it doesn't add up to anything meaningful, the series diverges. However, if I take the absolute values away, then it makes sense. This is called conditional convergence. It's very important that we know between the two because there are times when absolute convergence means that we can do things when conditional convergence means we can't. For example, very important, absolute convergence gives us commutativity of addition with infinite sums. If we have a conditionally convergent sum, then if you rearrange the order, you can get different answers. And that is problematic, especially when we want to like distribute integrals or derivatives across a sum. If we can rearrange the terms and the sum can change value, then the integral and the derivative and everything else we want to do would change value. And that's no bueno. Okay. Properties of series, they are a lot more fickle than sequences. Not a lot of things work with them. We can factor out constants and we can distribute them across sums, but almost everything else is not going to work. They do not distribute across products. They do not distribute across divisions. They don't go inside of powers, etc. There's the idea of a telescoping series, but we actually skipped that. Okay, so that was just series, the sum of the terms of a sequence. However, you might realize that this sort of process that we went through here is kind of annoying to go through. And that led us to the next set of topics called the series convergence tests. Sometimes actually figuring out what a sum converges to is very, very difficult. So while we might have methods that we can use to determine that, one thing that's important to know is that a series converges at all, right? If you know that the answer is out there, then it's worth looking for the answer. If you realize that the answer isn't out there, then you shouldn't look for the answer, like it doesn't converge, right? So there are some tests that will tell us that a series converges. They don't necessarily tell us to what it converges. So for example, in our previous example with the dichotomy paradox, we saw that the series converged to 1. It's possible for us to know that it converged, but not to know that it converged to 1, right? It would depend on the example. So we have these series convergence tests. And basically what these guys are going to do is they will tell us whether or not a series converges. And that will tell you if there's a meaningful answer out there that's worth looking for. And you have to do some other trick to actually get to that answer. And we will see how to do that with a few examples, but not nearly as general as we could be. Okay, so far we covered 5 of these tests. Okay, so we looked at first the divergence test, which is the first thing that you should know. That's the guy that tells you when a series diverges. It cannot tell you about convergence. So if you realize that the limit of the sequence term is non-zero, then the series will diverge. Geometric series, these are series with a very specific form. So they either look like that, or you can start them at 1 and then look like k minus 1. But the idea is, you know, a is the first term and you keep multiplying that by r. A and r are constants and they're non-zero. So they have a very specific form. We know that those converge, and in fact, we know what those converge to. They converge to a over 1 minus r if our r is less than 1 in absolute values. They will diverge if your r is greater than or equal to 1 in absolute value, right? So this is one of the few tests that actually tells you what something converges to. That's very rare. This test and the telescoping series test actually tells you that, but this is the only one that we're covering in this class that actually tells you what the exact answer is. All the others, they don't tell you what the answer is, they just tell you that there is an answer. We also saw the integral test. Basically, if we're finding the series of some term ak, and we realize that if I interpret that ak as a function, the corresponding improper integral will converge or diverge, then the series is actually going to behave the same. There are some conditions though. Your function has to be continuous on the interval, and it has to be decreasing on the interval, at least eventually decreasing, and the function needs to be non-negative. You cannot decrease below the x-axis. There's also the p-series test. We actually use the integral test to actually prove that. And so basically any series that looks like this, it will converge if your p is greater than 1, and it will diverge if your p is less than or equal to 1. Then, just like with improper integrals, again, because of the integral test, we can actually compare series. So we had the direct comparison test, which behaves very analogously to the direct comparison test that we had for improper integrals. The same sort of idea holds for series. Okay, and we did all of those guys and did lots of examples. We mentioned a very famous example, the harmonic series. That guy's known to diverge even though the limit approaches 0. So that tells you that knowing that the limit approaches 0 does not tell you whether the series converges. So you have to be very careful. The test for divergence only tells you about divergence. Go figure. Okay, so we did a bunch of examples. Here are examples on the geometric series. Examples for the integral test. Examples for the p-series, and examples for the comparison test. And the same intuition, like I said, the same intuition that you had from limits in Calc 1, as well as what we're doing from improper integrals in this class, you can use the same kind of notions to actually do the comparisons. So one way in which p-series are very useful is that they're always often, not always, but in this class, they're often useful in making comparisons, right? So while a p-series by itself is very trivial to actually know whether it converges or not, the point is usually not to determine this with a p-series, but to determine it with something much more complicated that we can compare to a p-series. The p-series just gives us a very easy way to determine convergence based on comparison. All right, and that's kind of where we ended up last week. So we are going to continue with another comparison, which is actually very, again, very analogous to the kind of comparison that we had for improper integrals, right? If I had two sequences, an and bn, they're both positive for all n, and I take the limit of their ratio and I get a positive number, right? So positive real number, then the series of an and the series of bn will both converge or both diverge. They will behave together. Once this limit here is proportional. There are actually a few more items to the limit comparison test, but this is the only one I expect you to know. There's also the idea of well, if the limit of an over bn equals 0 and bn converges, bn converges, then an converges. And there's another item that says if the limit of an over bn is infinite and your bn diverges, then your an also diverges. You don't need to know that. But just for the sake of completeness, just so you know, no one can accuse me that I never told you the full limit comparison theorem, right? So the full theorem has like 3 items to it, but I only expect you to know one, the one that is analogous to improper integrals, okay? So that being said, the intuition, like I said, is very, very similar to that of improper integrals. So nothing really much more to say here. Let's actually just jump into an example. Let's determine whether or not this series converges. And I think you guys have all the notes for this section already, so you guys don't have to copy anything down. Let's actually just jump into it. So remember when we wanted to look at these guys and want to do comparison, what is the thing that we look at first?
The powers.
The powers. And which powers do we care about?
The highest one in each.
The highest
numerator
powers.
and the
So you kind of you focus on this guy, right? So your idea is you want to compare to like this series. Which is actually just the series of 1 over n. Okay, so now remember with the direct comparison, we had to know who's bigger than who. However, in this case, you'll notice something. So if I set, if an equals the original, n plus 10 over n squared plus 2n plus 3, and bn equals 1 over n, I can ask the question, is an greater than or equal to bn, or bn greater than or equal to an? And it turns out in this case, here, we're not sure. At least not sure without extra work. Right, I mean, you could probably figure it out, but it'll probably take more. It'll probably take more work than you'd want to do. So you're not sure. Why are you not sure? Because you'll notice, note, to go from an to bn, we, on one hand, made numerator smaller, which indicates that bn should be smaller. Right? I subtracted 10 from the numerator, right? The numerator went from n plus 10 to just n, right? But also what you'll notice is that we also made the denominator smaller. Which means bn should be larger. And now it's like, well, who wins? You know what I mean? So at this point, because we made a change that was in changes that were in conflict, we're not sure who wins out, right? So we made the numerator smaller and we made the denominator smaller. And so now, at least without further calculations, it's not, you don't know who wins out. Does changing the numerator make it smaller than changing the denominator made it bigger, or vice versa, right? It's not directly clear at this point, right? So it's not, right? It's not very clear. So the direct comparison theorem is going to be a little bit annoying to use here, because to apply that, I would need to know who's bigger than who. And I would need to know that the bigger one converges or the smaller one diverges, right? So the direct comparison theorem is very specific and very peculiar. However, here, once I found the optimal thing to actually compare to, it's not clear who's bigger than who, right? So I do know that this guy that I want to compare to diverges, but I don't know, is it smaller and it diverges? So what I can do here is instead apply the limit comparison test. So notice that an, bn are positive, and if I take the limit of an over bn, this is going to be the limit It's going to be that limit. And what is that limit?
1.
1, which is greater than 0. So this means AN and BN both converge or diverge. And since BN diverges, it's harmonic. Right? It's a harmonic series. This means AN diverges by limit comparison. So like I said, when you're using the direct comparison theorem, you can just say comparison. When you're using the limit comparison theorem, you usually emphasize that you're using the limit comparison theorem. You say limit comparison. So comparison is just direct comparison theorem, right? So it turns out that this guy diverges because he behaves very similarly to the harmonic series. Too similarly to the harmonic series. In fact, how you can interpret this limit is kind of like a constant of proportionality, in fact. So proportionately, they're both the same. And so one doesn't give you an answer, the other one is not going to give you an answer either. Okay. So hopefully that's clear. That's the limit comparison theorem. Or we call it the limit comparison test. Okay, so that's that. I don't think we need any more examples because it's very similar to improper integrals, comparison theorem from improper integrals. All right, let's move on to the 7th test. This test is called the alternating series test, and that's because it is a test that applies to things that we call alternating series. So what is an alternating series? This should probably be in bold. Okay, so an alternating series is a series in which the terms alternate in sign, right? And it means that you can write it in one of these two ways right here. Okay, so in the first way, notice that this is, oh, I actually mentioned it down here. So it's like a minus A1 plus A2 minus A3 plus A4 minus A5 plus A6 minus that, and just keeps going back and forth, right? That's actually this one right here. And if I go plus A1 minus A2 plus A3 minus A4 plus A5 minus A6, that's that one right there, right? So the signs alternate. You can start with a positive or a negative, it doesn't matter, but it just matters that the signs alternate. Now, how you actually can force the signs to alternate is you actually assume that your AN is always positive. So then when I multiply it by a positive or a negative sign, the sign doesn't change on me. So if AN by itself only produces positive terms and I hit it in front with this -1 to the n, which we saw a couple lectures ago, just alternate signs between plus or -1, this alternates the sign of the terms of the sequence. And so when I start adding them together, I'm adding a plus, then a minus, then a plus, then a minus, then a plus, then a minus. Signs alternate. We call this an alternating series. Now, the alternating series test is actually pretty easy and simple and very nice, coincidentally, right? So this is the alternating series test. Suppose you have an alternating series. If these two things occur, right? An alternating series means the AN terms are positive and then you're alternating signs. If AN is eventually decreasing and the limit is 0, then the series converges. That's it. So if the limit approaches 0, the series converges. Not the series converges to 0. I'm talking about the limit of the sequence converges to 0. Then the series, the alternating series will converge, providing provided that these guys are decreasing. And this is why we need to know about decreasing. So this test requires that you know that the terms are getting smaller and smaller over time. So you have to actually do that check. Okay. But once you have that check, the terms are decreasing and the limit approaches 0, your alternating series will converge. That being said, I want you to know about the type of convergence, which I have in red here. The alternating series test applies when we have plus, minus, plus, minus, plus, minus, which means if I were to throw in absolute values, I would kill all the minuses. And so the convergence that we're talking about here is not absolute. So when I talk about convergence here, this guarantees conditional convergence. Absolute convergence requires another test. Okay, so we'll talk about that in a little bit as well. So hold on, give me a second. I have to close this door. Okay, back. All right. So that's very important. So the alternating series test can only tell you about conditional convergence. The series may converge absolutely, but the alternating series test cannot tell you that it converges absolutely. It can only tell you about conditional convergence. Okay. So let's actually jump into some examples. Here's an example. Determine whether the following series converge. Okay. So here we have a series. It's -1 to the n over n. Notice that when I plug in n equals 1, I get -1 over 1. When I plug in n equals 2, I get positive a half. Plug in n equals 3, I get negative a third. Plug in n equals 4, I get positive a quarter, and so on. Right? So the signs are alternating. 1 over n gives me a positive number for every n greater than 1, greater than or equal to 1. However, the -1 to the n is just changing the sign, and it alternates every other term. Okay. So the question is, does this guy converge? This is a famous series. It's called the alternating harmonic series. Notice that it's just like a harmonic series, except the signs are changing. Now, here's what we can notice. So here we have the series of -1 to the n a n, where our a n is equal to 1 over n. Now, a n is positive for all n. 2. A n plus 1, well, that's just 1 over n plus 1. That is actually smaller than or equal to 1 over n, which is a n. So a n is decreasing. Right? At this point, that's a pretty obvious one. 1 over n plus 1 is less than or equal to 1 over n because the denominator on the left is larger. Alternatively, I could say that show that a n prime, well, this is -1 over n squared, and that's always negative. So this thing is positive, it's decreasing. And finally, if I take the limit of an, I get 0. Therefore, an converges, at least conditionally. So that's it. That's the alternating series test. Once your terms are positives, so we're guaranteed alternating signs. Your series is decreasing, and it doesn't have to be decreasing on the whole thing, but eventually decreasing. Meaning, in the beginning, can do whatever it wants, but there must come a point where, after that point, every term is smaller than the previous one, right? So that's what eventually decreasing means. And if the limit goes to 0 under these conditions, then the alternating series converges. At least it converges conditionally. It might converge absolutely. That being said, let's actually talk about that. What would happen if we put absolute values around each term?
Wouldn't it just mirror 1 over n, which we know diverges?
Exactly. So here, so what you would do is you would consider right. So you go into the series and you put absolute values around the terms. Right. You'll notice that you'll notice that what that does is it just gives you the harmonic series. You literally just get the series with 1 over n. This diverges. This means the series minus 1 to the n over n converges conditionally. Right? So this is where we're starting to see, we'll do more practice on something like this, but we're starting to see the difference between absolute convergence and conditional convergence. Basically, conditional convergence means it does not converge absolutely, meaning if I put absolute values, it doesn't converge. However, if I take them away, then it does converge, right? So such a series is called a conditionally convergent series. So the alternating harmonic series converges conditionally. In fact, and I believe in this class, this is actually something we're going to see. It's going to be really cool. We're actually going to prove this at some point. Guess what that guy adds up to? Super obvious. Minus ln2. We'll see why in a bit. In a couple lectures, we'll actually see why. But that actually converges to minus ln2. So it's another case where we're adding up an infinite number of rational terms, but we end up with something irrational. So yeah. Very famous example, the alternating harmonic series. Okay. And that's basically alternating series there. That's, again, this is a very easy test. There's nothing, we'll see more examples for sure later on. We're going to actually put this all together. But for now, I think that little intro to the alternating series test is actually good enough. So just make sure your terms are positive, so you actually guaranteed an alternating sign, show that they're eventually decreasing, and then show that the limit is 0, and then the alternating series converges at least conditionally. If you want to know whether it converges absolutely, What you would then do is you remove the alternating signs, just make sure everyone is positive, and then see what happens, right? If it no longer converges, then you know it converges conditionally. If it also converges with the absolute values, then you say it converges absolutely. We'll do more practice on absolute versus conditional convergence later, but slowly introducing you to the concepts here. Here's a very nice test, very important test, the ratio test. And this test is important for a bunch of reasons because there are a bunch of situations outside of just testing whether a series converges where we're going to be using the ratio test. So when we get to power series and things of that sort, we're going to be using the ratio test to do a lot of things there as well. So ratio test, very important test. In general, this can be applied to any series. However, it's particularly useful in these scenarios when you have factorials or exponentials. Okay, so we spoke about what a factorial is already. So chances are, if you see a series and there are a bunch of factorials all over the place, you don't even know how to integrate a factorial, really, right? So you wouldn't do the integral test or something like that. Maybe you can do a comparison test, but if all else fails, you see factorials or something, or just a lot of crazy exponentials all around the place, the ratio test is going to be a good test to try, right? Not guaranteed to work out, but it's a good test to try. It tends to be useful there, right? It is not useful for rational functions. I should just mention that. And we'll see why later, but actually the test itself can tell you why. But let me I'll talk about it later as well. So this is the ratio test. You guys can take a picture if you don't have the notes printed out or something. So here's what it says, right? AN is an infinite series. The only requirement is that none of the terms are zero, but they can be positive or negative. We don't care as long as they're not zero, because we're going to be creating a ratio and we're going to be dividing by AN. So that's why we can't have them zero. Set this limit, the limit of, as n goes to infinity, of the absolute value of AN plus 1 over AN. Then you have three possibilities. If your L, if your limit is a number less than 1, then the series converges absolutely. And that's super important. That's super nice. This test, if it works out, it actually works out in the best possible way. It actually converges absolutely. Any series that you have used the ratio test to prove it converges, you get absolute convergence for free, which is very nice. If your limit L is a number larger than 1, then it turns out that the series will diverge. If we're in the situation where the limit is equal to 1 exactly, then no conclusion. You're kind of in a situation where you don't know. You need to use a different test because it's possible for it can go either way. So for example, L equals 1 for both the harmonic series and 1 over n squared. And we know that 1 diverges while 1 converges. So when the when the limit is 1, you can't tell, right? So you need to do something else if you end up with a limit of 1. However, in all other scenarios, it's either going to be bigger than 1 or less than 1. In the event that it is less than 1, that means that it actually converges absolutely. If the limit is greater than 1, then it diverges. So I'll talk about why it's actually useful to use this when we have factorials, as well as why it doesn't work in the case of rational expressions. You'll notice that 1 over n as well as 1 over n squared are rational expressions. So let's actually look at a couple examples. Okay, so here is an example. Series n goes from 1 to infinity of -1 to the n times n all over 2 to the n. Determine whether this guy converges or converges absolutely. Okay, so how would you do this? Well, what you can notice here is you can take take an equals the whole thing. Right? I'm not thinking of it as an alternating series right now. I actually want to know whether it converges absolutely. The alternating series test cannot tell me that it converges absolutely. So take an to be that, right? So this means that your an plus 1 is going to be, I'm going to replace all the n's with n plus 1s. This means if I define this limit as n approaches infinity of an plus 1 over an, which, by the way, it's often convenient to think of this as an plus 1 times 1 over an, specifically as an plus 1 times the reciprocal of the original. So this would be -1 to the n plus 1, n plus 1 over 2 to the n plus 1 times 2 to the n over -1 to the n. Now, there are a couple things that we can do here. So this here is an optional step. But if you find that you're someone who would get confused with all the symbols moving around the place, this is often a very nice thing to do. Group like terms together. So I'm going to put the -1 to the n's together. I can put the polynomials together, and then I can put the exponentials together. It's easier to see how things will simplify, and you're not going to miss anything. Separate like terms so you don't miss any. Separate like terms so that you don't miss any simplifications. Okay, which is not completely necessary, but you might find it helpful to do that. Okay, now also you're going to see a bunch of things happening here. So now what you will realize is that certain things would start to cancel, like -1 to the n is going to cancel into that. 2 to the n is going to cancel all of that. And so what you're going to have is you're going to have the limit of -1 times n plus 1 over n times 1 over 2. Okay. It also tells you, by the way, that you can actually ignore so now this also another pro tip here. Because of the absolute values, we can ignore negative or alternating signs. In this test. Right. So here, notice that I put the -1 to the n inside everything just to like follow the definition and just plug in everybody. But you could actually just ignore the -1 to the n there, right? Because once you're throwing in the absolute values, it's going to die anyway, right? Which we see is clearly happening here. Okay. So now we have this. What is this limit?
One half.
It's a half. Nice thing about a half is it's actually less than 1. What that means is, does the series converge or diverge?
Convergence, absolutely.
Converges, not just converges, but it converges absolutely. Absolutely it converges. Does it converge? Absolutely. This series converges absolutely. Meaning the alternating sign is irrelevant. I could have just taken away all the negative signs. It still converged. Right? That kind of goes to show you just how much more exponentials are bigger than polynomials. The denominator is growing so huge that eventually it's like you're adding nothing. Even whether you're adding positive or negatives, it's like you're almost adding zeros after a while, because the polynomial compared to the exponential is like nothing. So yeah, so this is the ratio test. You pretty much compute this limit right here. You can rearrange terms to make it a little easier so you can see how things will simplify. But then at the end of the day, if you get a less than 1, it converges absolutely. If you get a greater than 1, it is going to diverge. If you get equal to 1, no conclusion, right? It can actually go either way. So you need another test actually. Let's do another example. Okay, so this one, does this guy converge or diverge or absolutely? What do you think? What are your thoughts?
Could we do a comparison test to the previous one that we just did, saying that e to the n is greater than 2 to the n, and thus this one would also converge because it's smaller than the other one?
Is it? No, you're missing something. Read carefully.
Oh, the exclamation point thingy.
Yeah, the exclamation point. It's not excitement. It actually it means something. No. What do you think now? Would it still converge? What do you think?
I think we need to try and use the ratio test.
You should be able to tell. Any predictions before going into the ratio test?
So doesn't like infinity factorial out trump everything? So
Well, it doesn't out trump everything.
well,
Like n
anything
to the
in
n
that
would be larger.
fraction,
Huh?
e to the n would be larger.
No. So what was the
So,
hierarchy?
well, looks like it's an alternating series that doesn't approach zero, so I don't think you can tell if it converges by that.
Well, what if I were to just look at the limit of n factorial over e to the n? What is that?
Infinity?
That's infinity. What does that mean? I take the limit and it approaches infinity. What does that mean?
Would it diverge?
The series diverges. How do you know?
Because infinity is bigger than 1? Is that, no, that's the test. I don't know.
Why does it diverge? Who tells us this diverges because the limit is infinity? By
comparison.
how we didn't compare it to anything. I just took the limit.
You're just talking about that sequence on its own. Never mind.
Yeah, like I didn't compare it to anybody.
Divergence test because it's not equal to 0.
By the test for divergence. Right? Remember, that's the easiest test. It should be the one that's always on the top of your mind. Before you even do anything, one of the first things you should be checking is the divergence test. If the limit is not 0, it diverges, right? Now, if you don't, someone got kicked out of the room here. I think he's back. Right? That's the test for divergence, right? If the limit is not 0, it diverges, which means if you try to go and do anything else, it's literally a waste of time. Every other test is going to tell you it diverges or be inconclusive when it's like you didn't even have to go through any other test. Test for divergence. Remember, the limit has to approach 0 to have a chance of converging. It doesn't guarantee it will converge, but if it doesn't go to 0, then it definitely diverges, right? So just right off the bat, and I know right now I'm illustrating the ratio test. However, if this were on an actual test or a quiz, I would expect you to know within a few seconds that this guy diverged and not waste your time with anything else, okay? However, we will still do the ratio test just for demonstration purposes. But it is overkill. So overkill for this problem. That is the better method by far. Okay. So again, your intuition from limits, very important. Just knowing that the factorial is going to outgrow the exponential, you can look at this and know it's going to diverge. You don't really have to do anything. But let's just continue with the ratio test just because I actually want to actually show you guys something, why the ratio test might be useful, but let's actually just jump into it. So yeah, so my AN, what I'm doing is set AN equals n factorial over e to the n. As I discussed earlier, I can ignore the alternating signs because I'm going to throw this in absolute values anyway. And I can say let L equals the limit of an plus 1 over an. So remember what this looks like? I'm going to just put an plus 1. Then I'm going to multiply by the reciprocal of the original. Rearrange the terms. This simplifies that. What about the factorials? N plus 1 factorial divided by n factorial. What is that?
You can rewrite n plus 1 factorial as n plus 1 times n factorial, which would cancel with the bottom. So it's just n plus 1 on the top.
Right. And that's because if you look at this part here, this is n plus 1 times n factorial over n factorial. So the n factorials cancel. Right? Because remember, n plus 1 factorial is just n plus 1 times n minus 1 times n minus 2 times n, go all the way down to 1. And n factorial is n times n minus 1 times n minus 2, all the way down to 1. They're the same after a while, right? So this is why the ratio test is super convenient for factorials. Because you're taking the ratio of factorials, you can, after some point, cancel everything out, right? So this is why it's actually very useful. However, at the end of the day, you have the limit of n plus 1 over e. And as n approaches infinity, well, that's infinity. And unfortunately, that's bigger than 1. So the series diverges. Now, of course, I could have told you that from the very beginning within a few seconds, but you can actually go through a longer route to actually determine that the series diverges as well. So the reason why I still wanted to go through this example, even though we can know it diverges, and I just wanted another excuse to remind you how you should start looking at things. This actually shows you why. This illustrates why the ratio test is useful when factorials are involved. You'll likely get a lot of convenient cancellations. I can give you another example. Let's say we have the series n goes from 0 to infinity of minus 1 to the n over 2n plus 1 factorial, right? So you see something like that. The limit approaches 0, so we don't know whether or not it diverges for sure. We don't know whether or not it converges, so I know it. So the limit goes to 0. Let's say I'm interested in absolute convergence, so I don't want to apply the alternating series test. So someone asked me, does this converge absolutely? Which means the alternating series test is now off the table, right? So now, what can I use? The integral test? Do you know how to integrate a factorial? Well, I don't think any Calc 2 student knows that at this point. You'll need another class where you learn about the gamma functions, things like that to integrate factorials. So what are you going to do? Well, the fact that there's a factorial there and the test for divergence doesn't help, should make you think of the ratio test next. So what we can do here is apply the ratio test. Or couldn't. So we set L, this is going to be the limit of notice that we need parentheses here. And in fact, I can completely ignore these guys. I mean, they're not going to matter. But of course, now what you'll realize, what did I do? Now what you'll realize is that I would end up with 2n plus 1 factorial over, this will be 2n plus 3 factorial. Okay, someone quickly work that out and tell me what you get.
Is that 1 over 2n plus 2 times 2 over n plus 3?
Two n plus 2 times 2n plus 3. Oh, you turn them around. Okay. Yeah, that's what you would get. Because of course this, what that is, this is 2n plus 1 times 2n times 2n minus 1 times 2n minus 2, dot, 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 going all the way down to 3 times 2 times 1, right? Over this guy here is 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, dot, 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 all the way down to 3 times 2 times 1. What you realize is that this is going to cancel that, this cancels that, this cancels that, this cancels that, and they all cancel out. And because of the ratio, now all these guys cancel out and I only have a few terms left over, right? Which is the 2 that we have here. Now, clearly what you can see here is that that limit is going to approach 0, which is less than 1. And so the series converges absolutely. Right, so that illustrates to you why the factorial, whenever you see factorials, the ratio test is a very useful test to use, right? So the ratio test, there are a couple of reasons why you'd use it. If you want to know absolute convergence, and if you want to know if you see factorials or exponentials around. This also illustrates why the ratio test does not work for rational expressions. Right? So let's say I had an AN that was a rational expression. So example, given a series AN, if AN is a polynomial, let's say it's an nth degree polynomial, then AN plus 1 is also an nth degree polynomial. Right? If I take a polynomial and I replace the variable with the variable plus 1, the highest power stays the same. And so that means if I take AN plus 1 divided by AN, it will approach 1, right? Because then you take the ratio of the leading coefficients. The leading coefficients are going to be the same. The highest power is going to be the same. You'll always actually get exactly 1 as the limit, right? So if you see that you have a ratio of polynomials, it doesn't work, right? A similar thing happens if an is irrational. Come on. It spazzed out on me. But you can see that. A similar thing happens if an is rational, right? Because the powers aren't going to change. So when you take the ratios, the leading coefficients will be the same. The highest power will be the same. So they'll always simplify to 1 in the limit, right? So don't use the ratio test if you have rationals. But they're very convenient for factorials. They do not work for rationals. Okay. So I know I'm a little bit out over time, but I just want to finish this last test. This is the last test we need to know. And then we're going to put them together in a concept here, which I would recommend that you read through this and try to work through it for Thursday and try these examples. But I'm going to do one more example of the last test that I want to do. And this is called the root test. It's called the root test because there's a root in it. There's a radical. There's an nth root. This guy is very convenient. This guy can work with anything, even when the an hits 0 at some point. The thing is, this is convenient. It's most convenient if you're looking at something to the power of n, or maybe to a linear power can work as well, because you can always factor off the pieces, right? So suppose an is an infinite sequence. What you compute is a limit, but you compute this limit. So instead of the ratio that we did before, you actually take the nth root of the absolute value of an. It turns out that conclusions very similar to the ratio test will take effect. If this limit is less than 1, then the series will converge absolutely. If it is greater than 1, the series diverges. If it's equal to 1, then no conclusion can be made. So this guy is very similar to the ratio test, except your limit is just a different limit, right? And this guy is probably not useful with factorials, because if you don't know how to deal with a factorial, you're not going to know how to deal with the nth root of a factorial. But if it has like the power n, where the nth root can cancel the nth power, that's going to be very useful and convenient. So I do want to say something here. So the conclusions are very similar, but you should be aware that the ratio test and the root test are even more similar than that. They actually go hand in hand, meaning they will give the same conclusions in all the same situations. So if you're in a situation where the ratio test is inconclusive, then it turns out that the root test would also be inconclusive. So if your ratio test doesn't work out, don't try the root test, try something else. And if your root test doesn't work out, don't try the ratio test, try something else, right? The ratio test and the root test, they will give you the same answers. They'll behave the same way. So they will both say something converges or diverges. They'll also be inconclusive in all the same scenarios. So with rational functions, the root test also will not work. You'll always get a limit of 1, right? So again, I mentioned here and I underlined it. The ratio and root tests are useless when you're looking at rational functions. They will behave very similarly in terms of the conclusions they can make, right? So if you only ever have to apply one of these tests, because if you apply one and it doesn't work, it doesn't help, the other one is not going to help. So that will be important in terms of strategy later, which we'll talk about in the next class, right? So here's an example. Determine whether the following series converges absolutely. Just because I see this guy with an nth power, he's right there, very nice nth power, I'm actually going to jump in and try the root test because I see that little nth power there. And again, I wouldn't want to integrate this or do anything like that. Comparison would probably also be kind of annoying. The ratio test could work, but we're looking at the root test right now, and the root test was probably even nicer. What I would do here is set my an equals this guy, 2n plus 1 over 7n minus 3 to the n. So here, if I let L equals the limit of the nth root of the absolute value of an, this is just going to be the limit of the nth root of the absolute value of 2n plus 1 over 7n minus 3 to the n. The nth root is going to cancel the nth power. And now I just have the limit of 2n plus 1 over 7n minus 3 in absolute values. What is that limit?
Two sevenths.
2/7. 2/7 happens to be less than 1. This means the series does converge, and it converges absolutely. And you can say by the ratio test, by the root test. Especially when in your work, I'd like you to indicate what test you're using. By the ratio test. Okay. So those are all the tests. We have 9 tests, sort of how we had about 9 integration techniques. Would have been 10 if we did telescoping series, but that's it. Those are all the tests I want to do. Next class, I'm going to start off with a discussion of determining absolute convergence versus conditional convergence, the interplay between the two. How do you actually go about answering a question like this from a strategy point of view? So if I specifically ask you determine whether it converges absolutely, conditionally, or diverges, you'd want a strategy for that. That's here. I would recommend that you read that through and actually try these examples for next time so that we can compare our answers. That'll be even better. Because students getting used to series because it's different. It feels or looks different from what we've been doing before. You're definitely going to want to get more practice in on that. So I would do that. But as for now, that's all I have for you today. So now we know all the series convergence tests. There are more, but in Calculus 2, these are the typical ones that are taught. But yeah, so these are all the ones that I expect you to know, and they are summarized in the table. So we're done all of these. Well, this one we'll do more next time, but yeah, for now we'll stop there. I will see you guys again. I'll post the notes. Try to work on the other problems for next class for Thursday, and that might even make you realize that, hey, maybe on the recitation, I should ask more about series because I really am missing something here. So you guys can do that. I know I have office hours with one of you right now, so I'll go straight into that. As for the rest of you, we'll end it there. So hopefully you guys followed. Thank you for your attention and your participation. And email me if you want to set up office hours for this week. It looks like tomorrow is the best time. So hopefully you can set something up then. That being said, good night. Have a good one. And I will see you guys in the next one. Ciao.